AA2198 joints under different artificial aging conditions. I will first motivate and explain the procedure, present the results, and finally conclude. Beginning with the technological problems, all traditional design of aircraft structures have been made by fastening differential structures with rivets. It is obvious that riveting increases structural weight. New trends involve joining techniques as to replace riveting with fusion welding. It is estimated that structural weight can be reduced by 50% and respectively caused by 30%. Lithium is a metallic element with low density, therefore it was introduced to aluminum alloys to reduce weight. Nevertheless, this attempt had some disadvantages, such as higher anisotropy and mechanical properties. Aluminum alloy 2198 is a third-generation alloy with copper and lithium addition, and is already used to the fuselage cabin skins. This alloy is a precipitate alloy. By this I mean that with natural aging or with artificial aging, the quasi-static properties are changing. We don't have only one mechanism, but we have 4 different. So that makes the situation more difficult. But the question is, why we need these precipitates? Because we need these precipitates because they are blocking the dislocations. By blocking the dislocations, you can increase strength and you can sacrifice ductility. The tensile mechanical properties of various artificial aging times was examined in the literature. Here we can see stress-strain curves with increasing artificially aging for up to 900 hours for the base material of 2198. More analytically, we can see that with increasing artificial aging up to 8 hours, yield stress continuously increases. This is characterized as an under-aging condition. A plateau can be noticed from 8 hours to 48 hours, which is characterized as a peak aging. While with a further increase of artificially aging, there is a decrease in yield stress, which is due to the course of the precipitates, and this is characterized by the over-aging condition. Continue with the experimental procedure. We investigate aluminum alloy 2198 with 5 mm thickness. After the optimization of the welding parameters, we apply post-welding heat treatment for 170 degrees, and then we extract microflat tensile specimens according to the specification. Then we have the microstructure analysis, the mechanical testing, and evaluation. The results of the experimental results, let's say, used as an input to the finite element model, and then again we had evaluations and the conclusions. For the welds, we used fiber laser machine with maximum 8 kilowatt power. Argon was used as a sealing gas, while aluminum silicon 4047 filler material was used. Here we can see also the optimized parameters that are used in the present investigation. This slide depicts the dimension of microflat tensile specimens according to the specification. The microflat tensile specimens were extracted horizontally from the fusion zone in 3 different positions, namely top line, middle, and bottom line. While from the heat-affected zone, the microflat tensile specimens were extracted vertically. For the artificial aging conditions, we used a furnace for 170 degrees, and we used 3 different artificially aging times in order to correspond to under-aging, to peak aging, and to over-aging condition. The mechanical tests were carried out at Helmholtz-Zentrum Hereon using a SVIG testing machine. And also we used a special design fixture that ensured the correct application of the load. Continue the analysis of the results. Here we can see a harness versus distance from the weld center for the top, middle, and bottom line. As we can see, top line present higher hardness in the fusion zone, while the middle line present a degrees of hardness in both fusion zone and heat-affected zone. Bottom line presents similar hardness results with the top line and with a slightly degrees of hardness in the fusion zone. For the middle line, and with increasing artificially aging times up to 98 hours, we can see that higher hardness can be noticed for 48 hours in peak aging condition, while similar hardness can be seen in the fusion zone for all aging conditions. Continue with the analysis of the results. We investigate heat-affected zone, and fusion zone. Between heat-affected zone and fusion zone, there is one more zone, the transmission zone. Transmission zone is also divided in two more zones, the partially melted zone and the aqueous zone. The aqueous zone contains aqueous grains with random crystal orientation, while next to aqueous zone, fusion zone, compose columnar grains, and in the center of the fusion zone, we can see aqueous dendritic grains. Here we can see intensity versus the distance of the cross-section for the ADX line analysis for the middle of the cross-section. It can be noticed that silicon is higher in the fusion zone, while in the heat-affected zone there is a decrease. Also, we can see copper, manganese, and iron. So from the radiation, So from the radiation exposure side to the welding root side, also silicon decreases. For the tensile stress strain curves, for the microflat tensile specimens from the heat-affected zone, we can see that it has higher yield stress and higher ductility when compared with the specimens from the fusion zone in the top, middle, and bottom. So, from the specimens in the top position present a higher strength of about 190 megapascal. The middle line presents slightly lower yield stress with an increase in ductility. And bottom specimens present also lower yield stress and higher ductility. So that means that the existence of the silicon in the fusion zone affects the local tensile mechanical properties. As a result, a decrease in strength and an increased ductility. So here we can see the yield stress results versus artificially aging times. Here we can see that the microflat tensile specimens from the heat-affected zone continuously increase up to 98 hours. For the specimens from the fusion zone in the top, there is an increase from 3 hours up to 98 hours, while in the middle is a continuously increase up to 98 hours. Different trend can be noticed for the bottom line, which present a continuously increase up to 48 hours and then decreases. For the total elongation at fracture, we can see that specimens from the heat-affected zone decreases from 13% to 5.7, but the specimens from the fusion zone present similar behavior, which also attains the minimum values of approximately 1.5%. So, a three-dimensional parametric finite element model of the weld was developed to evaluate the different welding geometries and geometrical imperfections. Due to the symmetry of the problem at hand, a quarter of the specimen was modeled. The previous mechanical properties were used as a input to each region. The parameters which were investigated were weld bed width, weld angle, excessive weld metal, incomplete field groove, and excessive penetration. Of course, the parameters are too many, so of course I'm not going to show you everything, but in the next slides, I will let's say, use the 85 degrees for all the results. I mean, the middle. Okay. here we can see the equivalent, the maximum equivalent strain versus the weld bed width for 0.5 nominal strain. As we can see here, with increasing artificially aging, nominal strain in the as welded condition present higher results. These results can be attributed, that it's lower, due to the strain localization and the lower yield stress that can be noticed in the upper region of the weld. Also here we can see for 1% nominal strength and 1.5. As you can see, here is an opposite trend. The as welded condition is almost present almost lower maximum strain results. I'm trying to be a little bit fast. Here we just kept, I don't know if you can see that, we just kept fixed the weld bed width in 2.25 with 85 degrees, and here you can see the incomplete field groove results for 0.5% nominal strain. As you can see, as welded is almost linear. It does not present any significant changes. But with increasing artificially aging, nominal strain increases with increasing safety imperfections. For the case of excessive weld metal, it's similar trend, let's say, with the as welded did not present any significant change, while for the 3 hours and the 98 hours there is a continuously increase of maximum strain with increasing the safe imperfection. While for the peak aging at 48 hours there is an increase up to 0.6, and then with a further increase the strain decreases. Finally, here we can see the excessive penetration that did not present any significant change. It's almost close to linear. But again, as welded, present higher strain results. It would be the last slide, sorry. Of course, here we can see that according to the geometrical imperfections, that always the position of the maximum strains in the bottom, in the lower region of the fusion zone, in the as welded condition, while with increasing artificially aging, the strain localization can be seen in the top region. To conclude, we have higher hardness in the top line and the lowest in the middle. Most important is that the silicon in the fusion zone affects the local mechanical properties. The higher yield stress results can be seen in the bottom line. And the most important about the final element results, of course, in the last slide you saw that the maximum strain was observed in the lower region, in the fusion zone, the as welded condition. But the post-welding heat treatment says not only the value, but also the position of the maximum strain. So it leads to a potential different failure mode between the different welding samples. So, thank you very much.
Thank you for your quite interesting presentations. We have 1 or 2 minutes. The audience has any questions.
I tried to present as clear as I can.
Yes, a lot of work, it's not easy.
Yes, I had a lot of parameters, so it was very difficult to just to pick some results to show you, to present today.
How do you optimize your parameters?
The laser beam welded parameters? Okay. We used, I'll go back, sorry for that. First of all, we just optimize the welding parameters without filler material in order to make a weld with the less defects. porosity, hot cracking, and all this. So we just play with the parameters like the welding velocity. Just a moment.
Computer's not so fast.
Yes, sorry. I will go like this, it will be easier. Yes, it will be easier. So, generally, we just, in order to make the optimization of the parameters, we just, first of all, we did it without filler material. So we played with the laser power and the welding velocity and heat input, of course, in order to produce weldings with the less defects, such as porosity and hot cracking. After that, that we found the optimized, let's say, parameter in the in the autogenous welding, then we just insert the filler material, and then we try again to do exactly the same to find the weld without pores and without crackings.
Thank you.
Thank you.
Okay, thank you.